you started out the chapter with talking about the counting principles. And the counting principle just says if you're making some choices, the number of total choices that you have has to do with each individual choice times the next choice. So in other words, if you were choosing, you were going on vacation and you decided you have 5 shirts and 3 pair of shorts. How many different ways can you wear those? 15. Okay, I have 5 choices here and 3 choices here. So the counting principle says the number of total choices you have would be 5 times 3. Okay, if I go, oh, well, I have got, let's see, I've got blue, I've got yellow, I've got green, I've got purple, and I have red. Okay, so if I'm going to draw a tree diagram, okay, blue, yellow, green, pink, or purple, and red, I'm not sure what we want to let the P stand for. Okay, so those are all my shirt choices. Then I come down here and I go, okay, I've got black, I've got brown, and I've got yellow. So I make that first choice on the shirt. I'm going to wear that blue shirt. Well, then I can wear black, brown, or yellow. But let's say I didn't choose the blue shirt. I chose the yellow shirt. Then again, my choices are black, brown, or yellow. Green shirt, same choices. Black, brown, yellow, black, brown, yellow, black, brown, yellow. Okay, there's my tree diagram. Okay, kind of done a little easily. But if you'll notice, there's 15 choices at the end. Okay, anything that they give you, you should be able to draw a tree diagram. This is just the basic counting principle. If you said John had 2 pairs of shoes, 1 black and 1 brown, and 3 different pairs of socks, brown, black, and navy, how many different ways could he combine his shoes and his socks? 6. Okay, does that make sense? Okay, that's a basic principle of just your counting principle. All right, what if, well, and that was all that first part. Then you moved on to the second part where you either had order or you didn't have order. So the counting principle gives you the first thing. Then the second part says, what if you have a permutation? And you go, the permutation has to do with arrangements, order, people standing in a line, people going to a theater. Now we can do it by hand, or we can do it using our calculator. So if we were going to go by hand, we go, let's say that there's 10 seats in a theater, and you have 5 people going into that theater. And so the first person walks in, and we'll let the lines be the people, okay? How many choices does that first person have for going into the theater? How many choices of seats do they have? 10. Okay, so they have 10 choices. But then they sit down. So the next one that comes in, how many choices do they have? 9. And the next one that comes in? 8. And the next one?
7.
And the next one?
6.
Okay, somebody do that out on their calculator for me. What'd you get?
3,628,800.
All right, I'm going to trust you on that. All right, the other way to do this is to look at it as the permutation of 10 things taken 5 at a time. Well, if you remember, the way a permutation is done, it's 10 factorial over 10 minus 5 factorial. Okay, you remember that? So this is 10 factorial over 5 factorial, which means I knock out everything from 5 down, because on the top, if I did this by hand, 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and on the bottom I have 5 times 4 times 3 times 2 times 1. Look. So I'm left with the same thing I did when I did it by hand. Okay, you're doing the exact same thing. One just uses the calculator and one has you visualize it. Okay, do you understand that it's the exact same thing? Now, if 10 people went into a movie theater and there were 10 chairs, then obviously it's going to be 10 factorial, because it's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But I'm only taking 5 people. This would be the permutation of 10 things taken 10 at a time, which actually gives you 10 factorial, because it's 10 factorial over 1. Okay, because that's what 10 minus 10 is 0. 0 factorial is 1. All right, so we're doing the exact same thing. So that has to do completely with order. If you don't have order, you do a similar thing, but it's called using what's the other one? It's not a permutation, it's a combination. Combination does not have to do with order. Now these were in 12-2. The combination is just you make a selection. Okay, so one of the things that you're going to have to do on the test is decide whether it's a permutation or a combination. And that is based on the words in your word problem. If you are sitting down in a row of chairs, that has order to it. If you're just selecting 4 fruit out of a fruit bowl, that doesn't have order. Okay? If you are selecting a president, a vice president, a secretary, and treasurer, that has order, because they're not all created equal. Okay? These might not all be created equal. These seats right here, the chosen spot might be this one, right next to the aisle. Okay? Because you can get out and you can get yourself some more popcorn. So those seats are not necessarily all created equal. If you go to grab 5 fruits out of a basket, they're all created equal. You're going to eat all 5 of them. Okay, one is not better than another.
One's rotten.
Well, yeah, we're going to assume it's not. Okay, I want you to, now we're not doing probability. Okay, this was not probability yet. This was at the front end of the chapter where you were just doing the number of possibilities, like the bottom of the probability thing. So I want you to just real quick tell me the answer to this problem. A committee of 3 is selected from Jillian, Miles, Mark, and Nakia. How many committees of 2 boys and 1 girl can be selected? Okay, these are the names. Okay, these are girls, those are boys, okay? And you want a committee of 3, you're selecting 3, and you want to know the number of ways you can get 2 boys and 1 girl. Okay, you're not doing a probability, it's not a probability, just the number of ways that you can do that. Got it? Okay, you could do it with combinations. Okay, there's no order here, so it's combinations. You could do it with combinations, that you have a combination of two things taken two at a time times a combination of two things taken one at a time. Okay? That'd work. I probably wouldn't have done that.
Just two.
It's just two, okay? And the reason why it's two is logically. Now, if you do this, you're going to get the number 2. So you can do it like this. You're multiplying those, okay? But logically, you're going to think, I only have 2 boys. So my committee can either be made up of those 2 boys and this girl, or those 2 boys and this girl. That's only 2 different ways. So this, almost all the way through this chapter, you can either do it logically, or you can do it by doing combinations and permutations, okay? It's not that you can't do it logically, or you can't do it this way. It's gonna depend on you. Some problems you might do it one way, some problems you might do it another, okay? All right, listen to this one. 5 cards are drawn from a standard deck of cards. How many different hands can consist of 4 queens, and 1 king? How many hands can consist of 4 queens and 1 king? Another one where you could do it logically, or you can do it with combinations. What'd you get?
4.
4. Okay. Again, it could be the combination of 4 things taken 4 at a time times the combination of 4 things taken 1 at a time. Or you can sit there and go, okay, well, I need all 4 queens. And anytime I do that, I need all 4 of them. But then I have 4 possibilities of kings. So I can have all 4 queens, and then I can have the king of diamonds. All 4 queens, then the king of spades. All 4, king of diamonds. All 4, and then the one of clubs. Okay, so it's 4 different ways. So logically, you could think in your mind, or you could do it out with combinations. Okay, we did also on these things, we did circular permutations. What do I mean by circular permutations? Y'all remember? If I said, how many ways can 6 students be set at a circular table? Okay, how many ways can 6 students be set at a circular table?
25.
Okay, well, it's
5
6
factorial.
factorial over 6. Because it doesn't matter where I put them.
120.
Okay, what is it?
120.
120, because it's 5 factorial. Okay, they can sit in 120 different arrangements, because I could, if you will, rotate the table. So if I've got 6 spots, okay, and let's say Joseph sits there, okay, and then I've got these guys all the way around here. Well, I can go, okay, get up and move 1 chair, and Joseph moves over here. Well, really, even though Joseph's in a different chair, they're in the same order. Okay, so that's why it's not 6 factorial, because Joseph could sit in each of those 6 chairs and have that order be totally the same if nothing else changes up. So that is your number that you have. There's 6 students, factorial divided by the number. That's if it's circular. Now, I could change this whole problem and go, well, this is like the golden chair, okay? That's the special chair. Now all the chairs are not created equal. So now I've got 6 factorial ways to do this, okay? Now it's no longer circular because not every chair is created equal. Now, there was also something called reflection. Do you remember what reflection was? If you can flip it over. Now, you can have a permutation with a reflection without it being circular. Okay? In other words, I'm trying to think, I don't know, I can't come up with something right now. Everything that I think of is circular, because like beads on a bracelet. Okay, if you flip the bracelet over, are you going to know that that bracelet is flipped over? I mean, it really has nothing to do with the look of that bracelet whatsoever. Keys, you can flip keys over. You cannot flip people over. So if I went back here to this thing, about 6 people sitting around a table, I would not advise you to flip these people over. So it's not reflection. Okay, it's just circular, but it's not reflection. If I have containers of pizza toppings, can I flip those over? No. Okay, it is an item that cannot be flipped. Okay? If I have coins, now I want you to think about this. If I have coins, can I flip the coins? No, because they're not the same on one side as what they are on the other. Okay, so coins cannot be flipped. Okay, think about what the item is and whether it can be flipped or not. Okay, so that was the whole thing about combinations and permutations. Then you got to the part about probabilities. Okay, probability, remember, is success over total. But we also talked about odds at the same time. How are odds different than probability?
That's over failure.
Okay, success over failure. So if they give me 1, I should be able to supply the other one. So if I said the probability of something is equal to 1/4, what would be the odds of that same thing?
1/3.
1/3. The top's going to stay the same. The bottom's going to be whatever I have to add to the 1 to get my 4. Because success plus failures is going to equal the total. Okay, every single time. Something is either considered successful or is considered a failure. If you made a bet on something, there's no in between. You're either going to win or you're not going to win. So you're either going to have success or you're going to have a failure. So if I said, let's do it the other way. Let's say I said the odds of something were 5 to 7. What would be the probability of that? What's going to go on the top?
It'd be 5.
Sorry about that. I wrote it
12.
wrong. The 5 is going to go on the top. The top is not going to change, but the bottom is going to be what? 12. Okay? Because that's going to be your total. I can't see it.